Bueno, esto es la avanzadilla, ¿no ves? Se va empezando aquí los nuevos, se va empezando de lo que viene. De Costa Rica, que se mueve entre 25 y 30 todo el año.
So good morning, everybody. Thank you for coming. So today's speaker is Simone Santoro, originally from Italy, but now celebrating 15 years in Spain. And the reason why he might look familiar to you is that he did his PhD here at EBD, and is now currently working at the university in Huelva with topics of capture, mark recapture, and detectability. So without further ado, Simone, the floor is yours.
Thank you very much. Thank you so much. Thank you so much for coming. It's a pleasure for me to see so many familiar faces from the time when I was working here. We are a small group at the Universidad de Huelva of mathematicians, expert in computer vision, expert in computer engineers, and also 3 or 4 ecologists. And we are working on this line of research that is applying camera trapping and artificial intelligence to monitor biodiversity. That is a line of research that is also interesting for other groups, much more well consolidated than us, with much more financial and human resources. We'll talk about that later. But I think that diversity is important also in research, and we will see why. So I won't go over the topic of the loss of biodiversity, because I know that the audience in this room is very aware of it. But I just would like to point out a problem we have to make evidence-based policies in conservation, that is the lack of good data. And we have many taxa for which we have not enough data to make good conservation status assessment, like, for example, it is the case of mammals. And we need to fill this gap. And that's why in the last 20 years, there has been a growth in the usage of other techniques to collect data in the field, like mobile sensor and the stationary sensors, for example, satellite, drones, and on-animal sensors that provide information on the environment, very often in real time. They provide information on the habitat changes, and they provide also information on wildlife populations and individual physiology and behavior. And on the other hand, we have stationary sensors like camera traps, that is the target of this talk, and bioacoustic sensors. And it is very important that the role is playing the community service, the community science, I mean citizen science, that is very useful for two reasons in this context. On one hand, they help by labeling images and videos, and on the other, they also provide many images useful for conservation. So the camera trapping actually dates back to the beginning of the last century, but in that moment, the goal was to make people aware of the importance of biodiversity, of nature, and on the importance and on the beauty of nature, nothing more than that. And they used tripwire activated cameras to detect motion. But in the last few years, with the advent of digital technology and with the development of passive infrared sensors to detect motion, we are much more advanced than now to use the camera traps, and camera traps now are very popular in ecology also because of their lower cost. Why do we like so much camera traps? Because they provide a tool that is non-invasive or minimally invasive to collect data in the field, and because it is quite cost-effective compared to other methods to take data in the field, like, for example, trapping or tracking. And it is also important because it provides, or it allows to get a very large-scale monitoring, both from the spatial and temporal point of view. And it provides 24/7 monitoring. That is something that for me resulted very interesting when Javier Calzada contacted me to participate in this project of camera trapping and artificial intelligence, because I saw the possibility of using this data to detect, to model the detectability. That is something I will talk later. And it also detects rare and elusive species, reduce the human bias in sampling, and it provides data on population size, distribution, species richness, and behavior. When I started the project, my naive idea was that we have a lot of camera traps there in the field, and we take a lot of data and we make a lot of inference. Actually, I cannot say that it is false. It is not, it's true, but it is much more complicated than I anticipated at that time. Why that? Because these are not data, I will repeat this several times, are images. And you have to store them, to organize them, to assign a unique ID, and so on. And you have to process them to translate them into data. And this is a workflow full of possible pitfalls where you can have problems, you can find new problems that you didn't anticipate. So the pain, this is just a short list of some of the issues and pitfalls possible that you can possibly find when you work in a camera trap. The camera placement can be difficult to optimize. You have very often technical failures of the cameras. It can be time-consuming to install and to monitor them, and the weather can affect seriously the visibility of your subjects. And this is the most important thing. They generate an impressive amount of images. So there are quite a few tools that you can use if you start the camera trap study. Many of these are in R. This is a short list of the package in R that can help you with the camera trap data. CamTrap R, that is a package that provides a workflow to transform your data, your images into data, and to store them in a convenient way to make analysis in other libraries. It also makes some preliminary analysis, maps of species richness, for example. Then you have CamTrap-DP, that is a new data package, very useful to make your data interoperable among different platforms. You have activity, that is to study the dial activity patterns and other things. And you have unmarked, that is used to make hierarchical models on data proceeding from camera traps when you have no individual recognition. However, these are still images. You need data. And to translate them into data, you have to label them. And labeling data can be easy, like the genet here. It can be difficult if you have some failure in your camera. It can be difficult if you have a foggy picture that is very, very frequent. You can have your subjects quite far. You can have an animal as where there is a rabbit here, completely camouflaged in the vegetation. And you can have a lot of empty photos that are costly to review. There are 3 systems to label images. You can do it by yourself. You can do it by using the help of citizen science, and you can do it by applying some kind of artificial intelligence. Actually, doing it by yourself rarely works. It depends much on the on the goals of your research project, but just to give you an idea, in 2.5 years, we have generated more than 4 million images in our camera trap studies. So reviewing those images is impossible, completely impossible. The citizen science might be very helpful. Here there are just 3 examples. Zooniverse, probably the most important platform of citizen science nowadays, with over 2 million registered users. And you have and it is very focused also in camera trap projects. There are a lot of projects, research projects here. You have iNaturalist, that is also a very important platform with 1.5 million registered users. It is not focused on camera trap images, but it can be helpful also to label images. And then I put here MammalWeb because I like it. It's a project they started in the United Kingdom, and I like their idea of using citizen science to label images, but also involving citizen scientists to rent them camera traps. They put them, the camera traps in their areas, and they are also gathering new images. This is an example of our project. We have a project there in Zooniverse, that is the Iberian Camera Trap project, with 18 classes, including no animal, unrecognizable, and human. And here you can see an example. For example, we have 2 red deer. So you can say red deer, and after you are asked how many individuals are in the picture. In this way, we are getting data on presence absence, but also count data that can be useful for abundance estimation. The third system is artificial intelligence, and we are working with a convolutional neural network model. That is what most of people working on computer vision is using, this kind of models. And they are a kind of deep learning models very well suited for images. And as they are deep learning models, they use neural networks with multiple layers. And as machine learning models, they have this peculiarity of learning from the data they process. And there are limitations and benefits of artificial intelligence for us. The computer vision is just, or artificial vision is just the name you use to say when you use artificial intelligence to label images, in this case. An interest for ecology is obvious. The number of pictures your camera trap study generates is impossible to classify by yourself, and you need some kind of automation. And the limitation, probably the stronger limitation nowadays, is that there is a barrier between us and them, between the ecologists and the computer vision experts, because we do not speak the same language, and we do not know how to use these methods, how do they work, actually. And in fact, I think that in the next years, many more students will be taught to use artificial intelligence methods in ecology. This is something that is already happening, for example, in the United States, and I think that it's probably the next future. I'd like to point out this trade-off that is a classical trade-off in machine learning. That is a trade-off between the number of classes your model has to identify and its applicability out of domain in other areas, not in the area where it has been trained. And you can see that if you have a very large number of classes, its generality is very low. So here I show you two examples of CNN models applied to camera traps. The mega detector that has been developed by a collaboration between the Smithsonian Institute and Microsoft, and is an open source and freely available model that you can use to classify 4 classes: animal, empty, human, and vehicle. And then this model, when it recognizes an object inside the picture, places a boundary box around it. And this boundary box can be very useful for other models to get data on the number of individuals present in the picture, and also to make artificial intelligence focusing on the part where it is just the subject you want to classify. On the other hand, there is this model, Wildlife Insights, the model that is used by Wildlife Insight, that is a platform to help you with your camera trap studies. This platform is the collaboration between Google and 30 NGOs. And in this case, you have the possibility of classifying up to more or less 1,300 classes. So it's on the other side of the CNN model. And this model has been trained with more than 30 million images, and they have 50 million records coming from 43 countries. Before I show you a comparison between these models, I would like just to refresh your memory about 2 simple concepts that are very useful in computer vision. That is, to assess, to evaluate the performance of a classifier. You have recall and precision. So suppose you have a set of images, and in some of them you have a red deer, for example. The percentage of picture of the picture with the red deer that are correctly classified as red deer, this is the recall, also called the sensitivity. Okay, so it's the percentage of times it finds the real class. The precision is once it has said that these photos are red deer, how many of them, which percentage are really red deer, actually red deer. And if you compare the performance between a subset of these 1,300 classes in Wildlife Insights with mega detector, just with animal and blank, that is the usage we do most of times of this model, you can see that, okay, Wildlife Insights do an excellent job in many cases, but if you see the column of recall, you can see that it can miss actually a lot of animals in your pictures. I think that this is important, this trade-off, to make you understand that a global solution like that it is trying to achieve wildlife insights cannot be the best solution for you. Not always. It depends very much on the goals of your project. But if you have a local convolutional CNN model, you probably achieve much better performance in the classification of the images. That is what happens with our CNN model and with the model developed recently by people in Montpellier, that they have 25 classes and it is focused on just on the French fauna. So there are also AI-powered platforms that help you with your camera trap studies, and at the same time they allow you to have some classification by their artificial intelligence models. There is Wildlife Insights, we talked about it before. There is Agouti, that is another platform, also very interesting. We will see later something more. Camelot, WildMe, Wildbook. Okay, this is just a short list. There are many others. This is the first thing you see when you are registered in a Wildlife Insight. So you can create a project, upload your images, okay, and accept the suggestions the artificial intelligence model gives you. And also it helps you somehow to manually tagging the images. And after it provides some analysis, I think that for the moment they are very simple analysis of map distribution and something like that. But I think they intend to do also occupancy models in their platform. Agouti is similar, but the difference is that you can select which artificial intelligence model you want to use on your data, and deep phone is available here, for example. And another difference, there are like 4 or 5, I think so, artificial intelligence models that you can use there. And the difference also is that the export data are exported in a CamTrapDP format, which is very useful for sharing. Finally, WildMe. It's interesting because it's a non-profit organization that develops software for open source software in ecology, and they have these wild books specific for given species, and they are able of doing individual recognition of some of these species. That is interesting, for example, for capture modeling. And they have even created a bot to detect species in social media files, images and videos. So far I've given you a brief introduction of what is the state of the art, and our project is just a part of this. We have started in 2020 with 35 cameras in the non-floodable zone of the park, and we check them every 2 months to change the battery if it is needed to replace the memory card. And now we have 60 randomly placed cameras because we obtained another funding in 2022. The camera traps we are using are Browning no glow. That means that when they take picture in the night, they do not use visible light. And we have set up them to take a sequence of 3 photos in a row with a delay of 1 second before the sensor it is activated again. And we are using 32 gigabyte cards that have proven useful to avoid filling up, except when there are very unfortunate combination of wind, vegetation, and curious animals. So this is our milestones as we see it. We have a fieldwork protocol that we have learned to do mainly by trial and error. We have an image processing protocol. Then we translate the images into data. We do our analysis. We get our results. And we want to do our data interoperable and available for sharing with other platforms. This is just a part of this workflow. And I wanted to show you that is quite complex and that it has required a lot of time to us to figure it out. Okay? At the beginning, we take the data in a certain way, and from the data we collect in the field, we collect 5 in our case, we do a spreadsheet with the range, the daytime range of each camera and session, and this data is the input of the other step where we check the consistency of each image with that information. If there is some mismatch, we have to correct the metadata of date and time, and we start it again. After we have another script, the scripts are in Python and in R, to make image resizing and to assign a unique ID to every photo, among others. Then we make a file, a spreadsheet of the images that will go to the citizen science project, maximum 5 photos for each event, for each sequence. And then we have another script to upload the images to the Zooniverse and another to send it to CNN labeling. So our labeling protocol, actually, when you have your processed photo, all of them are going to be labeled by the CNN model. Some of them are going to the citizen science project. When they are classified by the citizen scientists, we take these photos that are already stored in different folders, one for each species, and we very fastly review them. That is much faster process than if we do it from scratch. And then these error-free images classification are used for training the convolutional neural network model. So why we are interested in modeling this data with hierarchical models? Okay, we have a very simple example here of an index of abundance like this, an index of relative abundance. And you can be lucky, you can have a situation like this, but you can be unlucky and be completely unaware of that and have a situation like this, where actually your relative index is not reflecting the variation, spatiotemporal variation of your demographic parameter, of your parameter of interest, maybe abundance, maybe occupancy, whatever. So that's why in the last 20 years, there has been a profusion of new models under the umbrella of hierarchical modeling useful to model data from unmarked individuals. And one of these is the occupancy model, okay, where you can model, you can estimate the probability of occupancy, accounting for the imperfect detection. And for that, you need data that are replicated the sampling must be replicated in time and space. That is just what we get from our camera traps, because they are always in the field. If you have a long-term monitoring of your camera trap study, you can use also a dynamic or multi-season occupancy model where you can also estimate the probability of extinction, the probability of colonization, and relate these parameters, of course, to some covariate, for example. All of these always accounting for the imperfect detection. So you can also use many other models, like, for example, N-mixture models to get estimates of index of abundance, but our index is much more reliable because they are robust to the imperfect detectability. And this is a very good peculiarity of these models. You can add a layer to your observational process, to the part of the observational process, and you can account for misclassification. That is just what we want to do, because we have data that are error-free in their classification, and we have a lot of data, all the data we have, that they have some error in classification, that are the models, the classification of the artificial intelligence. So far, this is we are working on several things. I'm just going to give you a short snapshot of what we are doing now. We are working on a paper we are submitting next week that is about citizen science and artificial intelligence. We are just comparing the capability of these two systems of classification to make a good job. And we have seen that if you compare the classification for the species for which the model has been correctly trained, it is kind of surprising for me to see that you obtain fantastic values in the triangle is artificial intelligence, fantastic values for the artificial intelligence, where the citizen scientists that also are trained in our platform can do a bad job in some case, like for example, for the badger, the confidence interval is very big because there were just a few badger, and with the leopards, okay, also with cervids. And we have compared if there was some characteristic of the photo missed by citizen scientists but correctly identified by the artificial intelligence, and we have seen that most of them are nighttime photos. Here there are just a few examples of photos well identified by our CNN model and not by our citizen science project. Here there is a cervid, here there is a genet. Can be difficult to see, more in a screen of a laptop. Here there is a human. It is a nail, a finger. Here there is a badger. It is easy to understand that it is badger, but can be unfamiliar to the users we have recruited in our project. Here there is a rabbit, a leopard. And here there is a fox, also can be a red fox, can be also difficult to be spotted. And I don't know if you see it, but there is a wild boars. And the wild boars are here. It's not easy to see. So another problem another issue, another topic we are facing now, writing a paper right now, is on the presence of dogs in Doñana. We have seen a lot of dogs in our camera traps, and I think that we should be worried about that, because in two cases we have also seen with people, and we think that it should alert us, because it can be a serious threat to the wildlife in Doñana. Domestic dogs negatively interact with wildlife mainly by hunting. For example, could be hunting small mammals, leopards, nesting birds, whatever. They can compete, for example, with other carnivores. They can transmit diseases. For example, the canine distemper virus can be transmitted to lynxes. It can be very, very dangerous. And for wildlife disturbance, of course. What we have seen is that dogs have been detected in most of our cameras, many of our cameras, okay? And most of the time we have detected 33 different dogs in groups of 2 to 4 dogs. In this case, there were 5 dogs, okay? This is a picture taken close to the Laguna de Santa Olalla, and probably with poachers, I don't know. And if we see more or less on range by just doing simple minimum convex polygons of those dogs that have been located in more of 2 locations. We can see that they cover actually very large area. And there is this dog, this is a champion because it has been viewed 11 times over 272 days from the first to the last capture and on 7 different cameras. We are now studying the dial activity of dogs, and we have seen they are more active in the morning and in the afternoon. And we are comparing this activity, this dial activity, with other species that could be competing or being, for example, prey of dogs. And finally, this is something we are working now with the development of 4 prototypes that are deployed in the Lucio in El Bolín. And these devices contain a Raspberry Pi 4, and we have a PIR sensor that we use on the night photos, and a framing difference system during the daytime. I will show you what is it. These devices are capable of detecting the animal, classifying it on site, and if the detection is of a certain species, for example dogs, it sends the image either by GSM or by Wi-Fi, and the images and the alert, by the way, and it is working very, very well. This is how it works, the difference framing we are using during the daytime. Okay, when it detects the species, in this case Christian, it is you have your classification with the score, okay, and you can see it in your mobile, in your smartphone. Okay, so this is what we have done so far. Actually, we have not finished all the work we planned to do, but we are, I think, at a good point. And I wrote this, that our long-term goal is to develop a semi-automatic monitoring system that can be used in protected areas, combining camera traps, artificial intelligence, locally trained models, and the statistical analysis to model the imperfect detection and classification. So now we are getting closer. Thank you very much. And
thanks a lot, Simone. We have time for questions. Okay, I'll start then. I have several, actually. I wanted to ask you, so it's about the next step in your journey, but how challenging do you think it's going to be to standardize and share your data into other platforms? That was one of my questions. And the second one, I'm curious with the citizen science part, if you could tell us a little bit more in terms of how, because you say in Zooniverse, for instance, there's a lot of users, but there's also a lot of projects. So I'm wondering how easy it was for you. How did you reach out to the users to get a good community working on your project? And maybe I'll have another one for after.
Okay, yeah. The first question, yes, it is time consuming. You have to learn to handle many different tools, and it can be time consuming. We are a small group, and I must admit that it can be difficult to do it. We are trying to grow as a group to get more human resources. And anyway, it is feasible. There are many tools available for them. The package I mentioned, the CamTrap DP, is still a beta version, but it is already used, for example, in Agouti. And for the other question, I forgot to mention that our camera trap project that I started 1 year, almost 2 years ago, has classified 1 million images so far. So this is to answer your question that yes, there are many, many projects, but if you follow it and if you talk with the citizen scientists in the forum, I think that the people who is working in this project are very happy with us because we have a continuous contact and they can provide a really important quantity of data. Yeah.
Thank you. Next question. Yes.
Okay, thank you very much. I think it's an impressive amount of images, but I like something that you say. It's images, it's not data. And I would like to come up with, well, to see your opinion. I think that now there is a boom on little projects that they have a dozen cameras and they try to report. But you were mentioning that camera traps reduce the biases that you have in traditional field surveys. And I think that in many cases it's the opposite, that increases the bias because, well, you can have 5,000 pictures of the same fox being on the same shrub, and it's not more data points than just seeing a single observation, no? You are attached to single localities. In your case, you have 60 observation points, no? Yeah, you see 24 hours, but I was thinking that's an impressive amount of information. But I was looking on thinking about projects that have 5, 6, 10 cameras, and they try to get conclusions about activity patterns, population structure. Well, maybe you are seeing 10,000 times the same individual, and unless you have a reliable individual identification, that is kind of useless. And I think that there is a risk that using these camera traps basically gives a sense of reliability when it's not there. When you are seeing very biased information. What do you think about that? Is that a possibility?
I think you're right on the danger of using just a few locations to generalize your inference, you know, because it can happen something like that. I think that we should use more cameras, and I think that it would be better if we had more cameras in the same location. That is something that many groups are doing right now. Okay, that kind of control, for example, if you are looking always at the same, area. No? But if you compare it with the traditional sampling methods to monitor biodiversity, you can actually see, I think, that you are getting data that are much more informative because they are there all the time. When you do, for example, a transit and you see and you count, rabbits, or when you do your study to monitor with monitoring trucks, for example, you are just doing a snapshot of the system. It is a snapshot. One snapshot, and it is very difficult to understand if there is an issue with the detectability, for example. That is why I'm very interested. I was very interested in this project at the start, and I'm still interested for that reason. Because, for example, sometimes we go to the field at Doñana, and we go to exactly the same place 2 days in a row, and the first day we see 30 fallow deer, and the next day we see none. There is much variability that is completely stochastic that is accounted by this kind of monitoring. Anyway, I agree with you that you should be careful with your generalization of your inference. Yeah, sure.
Following that, well, I had 2 questions. One is whether there are systems that work well that you could recommend. We were trying Wildlife Insights and Agouti, and we found that it had plenty of mistakes. And the second is actually whether it is, rather trying to obtain a very high performance in terms of every camera being very accurate in finding in detecting correctly all the animals. Working on having detection curves that allows you to estimate the detection error, which will vary strongly between localities, and use that in the same way that you use with the distance or something like that. Because my worry is that depending on where you place the camera, you will have large differences in detection that you don't resolve by having very good method of identification, and that very often the biases you find in, for example, in detection by citizen science is related more to that error than to the method itself.
Okay, there are different things in this question to me. On one hand, Agouti and Wildlife Insights do a great job with their models, but this is something I tried to insist before, that actually I think it is necessary to have locally trained models. That it doesn't mean you have to take a model and train it on the set of your cameras. No, but on the same study system with the same species classes, for example, and you can achieve much higher performance values. That said, there is no perfect model. There won't be ever a model that never fails in a classification. And so the important thing here is that you have to think of a way of modeling your data, being aware of it, being aware that there is misclassification. And I think that the formula we have found here by having a subset of just a subset of data with error-free classifications, and all the data with some error in misclassification can be very useful if you use hierarchical models like models to model data uncertainty and get estimates of your parameter of interest, controlling for data uncertainty. I would not recommend ever to use your citizen science, or even worse, your artificial intelligence classifications to make your inference without accounting for the error in classification.
Set of samples reviewed by experts and estimate the error systematically on them.
Yeah, definitely. And regarding the other, in Agouti, for example, they are going to implement random encounter models and distance sampling models that can be used for abundance estimation from your camera traps.
More questions in the room? We have one.
Thank you, Simone, for the seminar. This is just a small question. How do you choose the thresholds in artificial intelligence? When you get the output, how do you decide where to set the thresholds? Or you work with the whole probability distributions that is coming out?
The thresholds of what? Of the...
For the classification.
Okay. Okay. We have created the formula to estimate the credibility of citizen science classification, and we are using this metric to make a filter of more credible or less credible classifications. And we also have a formula that is in the convolutional neural network that assign a value that is not exactly a probability, the softmax value. But the problem of the softmax value that it should inform you on how the CNN is happy with this classification, is convinced about this classification. But there is a problem because it is not very reliable. It can be, for example, 90-90, and it can be completely wrong. It is not proportional to our way of understanding the credibility of classification. So what we do is just using all the classification from the citizen science, and we make a very fast review of all these folders. it is very fast, much more faster than if you should do it from scratch, because the 75–80% of photos are just empty. So it's a big filter there. Yeah.
I have a question on YouTube from Agus Camacho. So it's thanking you for helping us understanding the powerful tool that you're using in biodiversity monitoring. And he's asking, so I'll just read this question. He'd like to know if your protocols include the obtention of data that are frequently stamped in the images, like time, temperature, etc. And then if that's the case, how are they then accessed in the Zooniverse platform?
I'm not sure to understand the question. If we are using, our model in citizen science or in or the artificial intelligence model?
I think in the citizen science.
Okay. In the citizen science, no. We have every image has its metadata with a timestamp. So you have date and time and location of every image. This is part of the big pre-processing part of the workflow. And so we don't ask them to give any information on that. And I know there are models, artificial intelligence models, that you could use to get this data out of the picture, but we don't need that. Yeah.
Duarte.
So the same way you have competition between the citizen science project and the AI algorithm, could you have competing AI algorithms, like multiple models, and then you do some kind of model leveraging or something like that? Or is that out of your, I mean, computationally very intensive and impossible to achieve it? Or would that be useful for, you know?
Okay, to ask the second part, the competition among AI models, the problem is the big barrier there is now between ecologists and computer vision experts. And I'm not totally clear about the answer I can give to this question. But I know conceptually how it works. And I know that the philosophy of the machine learning models is just competing among models. They are building again and again the model by changing the weights of the neural networks of multiple layers, and so they are competing among themselves, to put it in some way. Yeah.
But then if you use a model in a long project, if you use an AI model in a long project and you are giving classifications by experts every time to improve it, you have the problem that you will have different accuracy in different years along the project.
Yeah. In
a way, it will be a methodological problem. As you have 5 or 10 years, your late identifications should be much more accurate than the first ones.
I don't see it as a problem. I don't think it's a problem. I think that you have, you're right. The model can change because the model is continuously retraining every few months, is retrained with a new classification from the experts, and it is going to improve. It is going to improve. You have no problem if you are automatizing this process of getting the data, transforming them into the images, transforming them into data, making your analysis. And if this process is automatized and you are just changing the input to get your results, you are probably you are just improving the precision of your estimates. You should not be biasing your estimates if the model, the statistical model, is correctly built.
It's not a problem if you have error estimates throughout the process, so you can then use that in the uncertainty that you incorporate to models, isn't it?
Yeah, it is. You have your information and the uncertainty of your classification just by comparing the classification of artificial intelligence with the classification of a subset of all these by experts that are error-free. And if everything works well and if you are not doing mistakes in that, I don't think so. I wouldn't expect that. And the model, the statistical model, is correctly built. You should just improve should be just improving your precision.
So I have another question on YouTube, this time by Maria Panif. She also thanks you for the talk, and she wanted to know how much data you need to get robust abundance estimates, and if this has been done successfully.
Robust abundance estimates. I am not sure I'm able to give a number. There is an obvious thing that is the more the sample size, the more your precision in your estimates, of course. And unmixed model with, for example, if we use the unmixed model, if you use unmixed model with this data, with the count data, because we have count data from the citizen science project, but we also have count data from our mega detector that is part of our CNN model. So we have count data from both source of information. We are not yet done that part. We have not finished the part of the analysis, but our idea is of implementing models that account for the uncertainty both in the detection on detection and also in the count data. We want to try that.
Is there more question? I had a very quick one then, because you said your cameras are set to take 3 pictures consecutively, and then you only upload 5 images per event. So I was curious if the selection was done randomly or if you had to.
In depth. Yeah, because we have a sequence of 3 photos. The camera stops, wait just 1 second, and do another sequence. If you have a horse going in front of your cameras, we have a lot of sequential photos. So what we do there is just creating an event that is the number that are consecutive photos. They must be separated by more than 1.5 million. This is something we just decided by trial and error. And from this big event, that is the concatenation of several sequences, probably, we take the first 3 photos, 1 in the middle and 1 in the end, to cover. We are not uploading all the photos to the citizen science project because it would be impossible for them to digest,
Thank you. One last question? No? Okay. So I think we can close it. Thanks a lot, Simone.